Pluto is a far-off and secretive dwarf planet, which was once a member of our solar system's planetary family. However, recent surprising declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this cold world is on a potential impact course with Neptune. But how could this happen? And what might be the consequences of such a massive event? Are we witnessing a unique cosmic phenomenon? Or is there more to this looming cosmic crash? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly due to its peculiar orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about the potential dangerous impact between these two celestial bodies, which could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly eccentric shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to other planets. This inclination and eccentric nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually gets closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of space mechanics. The three-body problem in space involves figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all interact in a complex way. The terms azimuthal libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is an azimuthal libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another important aspect in this scenario is the VZK oscillation, named after three scientists, Vashkovsky, Zelinsky, and Kozyrev, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so strange. Despite Pluto's path seeming erratic, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even when things in space seem chaotic and random, certain patterns and rules keep everything in order. All these factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or go off course. This three-body problem helps us understand how these dynamics change due to the way these space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a big role in keeping Pluto's orbit safe and stable, and Saturn helps as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a very long time, even billions of years. So, it's like Neptune, Jupiter, and Saturn are working together to ensure Pluto keeps moving safely through space without running into trouble. These phenomena are crucial in the context of the universe for maintaining the order and consistency of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be thrown off their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly colliding with Neptune in the future, understanding its orbit is incredibly important. This gives us a clear picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Using simulations has been extremely helpful for scientists to figure out how Pluto moves in space. These simulations use complex math to imitate how Pluto and other space objects like Neptune pull on each other. By adjusting tiny details in the simulations, astronomers can see how even small changes can lead to huge contrast in where Pluto returns in the last part of the 1980s. These recreations showed something truly intriguing about Pluto's way. Despite the fact that it has things like AML and scope libration to keep it consistent, its circle can still be wild and flighty. If you start with just a minuscule difference in where Pluto is or how fast it's moving, over many years its path can end up looking truly different. Yet, even with this chaos, Pluto's circle remains stable for a long time, like billions of years. This means Pluto's venture around the Sun has a sort of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when it involves chaotic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide a solid means to understand and anticipate the future paths of celestial bodies, they also highlight the limits of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made great strides in understanding space, the case of Pluto reminds us how our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists just now raising concerns about a potential impact between Pluto and Neptune, despite all these complex forces working to prevent such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system. particularly the fascinating case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's position on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He sees the reclassification not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The intrigue of these uncertainties, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not just for academic curiosity, but for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a theoretical scenario, but a reminder of the dynamic and often turbulent nature of space. Kaku's futurist perspective pushes us to consider the broader implications of such events, from the impact on our understanding of the solar system to the potential need for future space interventions. Kaku's viewpoint highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but anticipating how they might change in the future. The potential collision between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational influences acting on them. As a result, direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable with our current understanding, it highlights the importance of continuous research and observation in astronomy. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring that we stay informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the erratic nature of celestial mechanics both point to the need for ongoing exploration and a flexible understanding of our universe. The potential collision scenario, while highlighting the dynamic and complex interactions within our solar system, ultimately reminds us of the vast and still mysterious areas in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe.